exercise number 4 about integral calculus now. So this is the combination of definite integrals with a substitution. Why is it? Well, I want to show you in the first place that it's very important and also useful to not only substitute the terms, the given terms, and of course the differential, everything expressed by the new variable, u, or however it's called, but please not to forget also the limits of integration must be replaced. It's very important to see that if I write down integral from 1 up to e or over or whatever over this function dx. So integral in the interval from 1 to e means this is the starting value for variable x, and this is the end value for variable x. So just imagine I would find a appropriate substitution using u only instead of x. And then I would not look here and forget that these are x values. It would just be plain wrong. Okay, so in the end, there would be something like sort of integral u squared du, and I would still write 1 to e. This is simply false because these are x values. I'm not allowed to use x limits when my variable is called u. So I have to replace them. Now, that's very important. And as I said before the recording, it has the big advantage that you never need to perform a resubstitution in this case. You can just insert the adjusted limit values in the primitive function expressed by your replacement variable u. You don't need to resubstitute by x again or for x. Okay, so let's do it. Well, now this is, honestly speaking, this is quite a simple standard substitution case. You should recognize that the inner function here is the natural logarithm, which is always the first idea to try and substitute the inner function. So the best idea is just to try and use the substitution u equals ln of x. If you do so, you remember that the derivative of the natural logarithm equals 1 over x. So that's the short method again. U gets du, ln x gets differentiated to be 1 over x, and then you place a differential of x behind. That's the quick method for building the differential version of the substitution, right? And so now we can replace, and that's what we have, luckily. Okay, we have 1 over x dx. We can replace it by du. Here it is, x below and dx in the basis line. So dx over x, you could say, is replaced by du. That's what I'm doing. Also, ln x is replaced by u, so I get u squared du. That's all. And now it's blue color. Very important. How do I adjust the limits? Well, it's easy, actually. You just go back to your substitution equation. Then you remember, this is a value of x, so that means x equals 1. Insert here. So then u equals ln of 1. We know that the ln of 1 is always ln of 1 is 0. Any log of 1 is always 0. That's what I mean, because a power 0 equals 1. That's well known. So it means that this value of x corresponds to u equals 0, and we have to place a 0 here. This time it means u equals 0 because u is the integration variable, right? Also, the upper limit, e, inserting here, this should be e. I hope you can see it. It's sometimes not so easy to recognize. Okay. Inserting here, u equals ln of e, since x equals e. So ln of e is 1, as we all know. E is the basis of the natural logarithm, and the logarithm of the basis is always equal to 1. Yeah, so I get 1 instead of e. That's it. I have to integrate from 0 to 1. What have we just done? We have started out asking what is the area between this interesting function and the x-axis in the range between 1 and e on the x-axis. This is a certain purely geometrical question we want to answer. Now, by using this substitution, we have successfully transformed the whole expression, the whole integral, the whole approach we have replaced the integral by a totally different other integral. So you know what this is? This would be the area between a standard parabola to the x-axis in the range from 0 to 1. It looks totally different. But what we're doing here is actually it's a correct transformation, which makes sure that what we're doing here as a geometrical transformation keeps the area the same. Okay, that's guaranteed. Although this looks totally different, it gets the correct result. Don't think that now we have at once we have done something which leads to a very different result. No, it turns out that since although this is geometrically speaking looks totally different than this one, they have the same area. That's the nice thing about it. Okay, so we just integrate u squared gets u cubed over 3, you know, a standard integration rule. So that's the primitive function in u, not expressed in x. We do not resubstitute, we just put vertical bar from 0 to 1. We use the fundamental theorem. We insert the upper limit first, so that is 1 over 3 times 1 cubed. Then we subtract the value at the lower bound, the lower limit, right, which is 1/3 times 0 cubed. So in the end, we get 1/3 minus 0. Okay, it's 1/3. That's the area. 1/3 area elements. You know that we don't use any physical units here. So 1/3 is the result for this definite integral. So it wasn't really difficult after all. Let's just look at the other one. Well, it should be sort of familiar to you. Quite surely you have already encountered this expression before. It's the square root of 1 minus x squared over dx. And this takes place between 0 and 1. So it's a definite integral again. Well, after solving it, it struck me that the reason why this was familiar to me, this term, was that it's quite a famous version of also again of the circular equation. I may start out with this consideration just for a second. Look here. You remember the, well, perhaps I should note it here. You all know this important equation, x squared plus y squared equals 1. This defines the unit circle around the origin, right? So this is a sketch of it. Now, if you isolate y, you suddenly get y equals plus or minus square root of 1 minus x squared. It turns out, actually, that this root expression, this modified root function, describes exactly the upper semicircle of the unit circle, this one. This is the curve. Also, for the minus sign, this describes the lower semicircle. That's it. So in altogether, this is separated in two terms. This is a possible description of the unit circle, a wonderful curve. And so it turns out what we're looking for is, because it takes place between 0 and 1, it's this shaded area here. And quite obviously, the result of this exercise must be the area of a quarter unit circle. Okay, a quarter of the unit circle. We all know that the formula for circle area is area equals pi times r squared, right? Archimedes constant pi times radius squared. But since this is just 1/4 of it, or now let's use the unit circle first. Pi times r squared, since r equals 1. So the unit circle has an area of pi. The whole area will be pi, right? Oh, sorry. That's clear. So what we're looking for is the area of a quarter of pi, and that's a quarter of this circle, which means it's a quarter of pi. It's pi over 4, and that's our result also. That's our answer. But we will find it in a special way, of course. So now what do we do? Well, okay, it would take me more time now. I just try and do it. Okay, one possible substitution is x equals cosine of u. Now you would say probably, why? There's no cosine, no sine. Why do I use this substitution? Well, it's I can say it's a question of experience. If you have recognized the relation to the unit circle, you know, this can also be put in the form of squared sum of sine and cosine. There are really very many different reasons for doing this. So it's not the only way to solve it. By the way, you could also use x equals sine of u and other things. But let's just agree to use it and try and see why it works. Okay. So if I do so, then differential x equals, you know, derivative of cosine of u is negative sine of u. Again, I forgot, times dx. That's it. And then also I can, sometimes it helps to also use the inverse substitution, which means isolating u, and quite obviously u equals arc cosine of x then. Now, again, if you should take your time and make sure that this substitution corresponds to a monotonous relation between x and u. That's because if I make perform such a replacement, I should make sure that I have a one-to-one relation between the two variables. Okay, you know, like bijective. It should be clear if I get a value of x and transform it to u, this should also work the way back and forth. And that's why we always demand monotony for such a substitution. And it turns out in this area where, look at here, it's quickly recognized that also this function is only defined when x is between negative and positive 1. You can also see it here, it describes the circle. Okay, x is in the range of -1 to +1. Otherwise, the square root would not be defined in the real domain. Okay, and that's why this is where we are. And what you see here is look at the axis. This is the x and this is the u. So this is the graphical version of the substitution. And this is the official curve of the arc cosine of x. Right, look here. So instead of y, I'm using u and telling you that it's monotonously decreasing. That's a fact. This is the arc cosine graph. Okay, so then now you see why it works. Because replacing x against cosine of u, I get square root of 1 minus cosine squared of u. Here dx, oh, let me see. Yeah, right. It's also, oh, here it is, right. In this form, you know, this is the inverse substitution, while this would be the direct substitution. Sometimes we start out expressing the old variable by a term of the new variable. In this case, you see it's a good idea, because I can replace the isolated differential dx directly for or against negative sine of u times dx. No, sorry, that was, yeah, of course, this must be du. You see, if I express x as a function of u, I may say, okay, differentiating x with respect to u gives me dx over du equals negative sine of u. And then I separate the differentials. Please note that this is the second kind of using a substitution, expressing the old as a term of the new variable. It's always possible, this way around or the other way around. Sorry, I didn't explain this before. Now, that's why I replace dx against negative sine of u times du here. Now, I would really have to argue that, okay, this is clear because using the unit circle equation, again, the fact that squared sum of cosine and sine is always equal to 1, I can say, this is exactly sine squared of u. That's fine. But then taking the square root, by the way, it's the positive square root of this squared expression, I would usually have to replace it, pulling the square, you know, taking the root, I'm sorry, taking the square root of the squared term, I would get sine of u directly, but with vertical bars. Look, here's a little example. You must be careful. Just consider, it could be the case that cosine of u is negative. Or here, sorry, sine of u would be negative. If I square a negative term and then take the positive square root, I transform a negative expression to a positive expression. So that in case this happens, that's the reason why when doing so, I have to put the vertical bars. Look at here. Take -7, square it, and then take the positive square root. You know that this is defined as to be the positive square root. Now, -7 squared equals 49, and the positive square root of 49 equals +7. So this is a case where a negative number by this operation transforms to a positive number. And that's why, in general, the square root of any expression squared equals absolute value of x, you see? In this special case, if x equals -7, the result is absolute value of -7, which is +7. This is correct. Leaving away the vertical bars would be possibly wrong. Okay. In this case, after all, we can leave them away. That's why I put them in red color. We can leave them away since looking here again and checking this, we find out that sine of u is anyway greater or equal than 0. And that's why nothing serious happens here. So you see, sometimes the details are important. Now we have the following: the minus extracted outside, then we have squared sine of u, sorry, sine squared of u, du. Then we may integrate here. I say handbook again because that's standard integral. Perhaps you solved it using product integration also. That's by standard. The primitive function, we can insert the limits. Oh, by the way, I forgot the most important point. This one, we wanted to adjust the limits. And since 0 is here, sorry, and even this is wrong, I would have to replace them already here. Did you see that? I have to say, I'm sorry that I'm taking too much time now, but I just have to finish this. Pi half up to 0 because I'm using u already here. You know what I mean and where it comes from? It's because 0 is in value for x. Looking here, I can just insert in this equation, and then I should know that the arc cosine of 0 equals pi over 2. Then for u, look here. If I take x equal to 0, I'm here, the red point here, okay, the red mark. And this means that u gets equal to pi half. You should, okay, you should know this, or yes, find out. You know that cosine of pi half equals 1, so that's just the inverse of this fact. Also, inserting 1 for x, I get the arc cosine of 1, which is equal to 0. Actually, you can see it here, x equals 1, u equals 0. And also it's simple because the cosine of 0 is equal to 1. That's why the arc cosine of 1 equals 0. So it's quite simple. Also, we find out, we perform a backward integration in the end. You see, pi half decreasing to 0, but that's okay, is it? Yeah, yeah, that's okay, since our integrand gets negative, and in the end we get something positive again. So it's quite a nice transformation. After all, inserting and checking and cleaning up, we find pi over 4 as a result. And this confirms our geometric consideration. The shaded area is a quarter of the unit circle. Okay, thank you.